Okay. Hi, welcome everyone. Oh, I didn't turn off my other camera. All right, welcome everyone. We have a nice new support for our class. So I'd like to introduce Son.
Yes.
Son. Okay, I think I said it right. So she is going to be a main person to be able to tutor. So anyone, if you want to, do you have your hours already decided?
Yeah.
Okay, go ahead and
Yeah, I guess the hours should be displayed on the website, but I'm not sure. I guess it'll be updated this week, so you can check it out by getting for it.
Are the hours on Canvas or the ECU website?
There's a ECE Canvas something, and if you go into it, there's a link or QR code, I guess.
so it's not been updated yet with her information on there, but it will also have Son's on there. And so she will have another link here, and you'll be able to either schedule direct meetings with her, or you'll be in the study area most likely.
Yeah. I'll be in the second floor in math. So yeah.
Yep, in MEB, in the second floor, it's the study area, if you're not familiar, between the labs and the main department office. So as you go from the labs and the advising suite towards the main office on that west side, off to the right, there's desks that are there. And when she's available in there, she'll put, it says ECE tutoring on it, on the table, and you're welcome to just go. But I wanted you guys to meet her, and awesome to have another support through the rest of the semester. So she can help you with homeworks. If you want to go and study there, do homework, she'll be able to help you.
Yeah, feel free to reach me out. Thank you.
All right, thank you so much.
Thank you.
All right. Where did the Zoom link go? Okay, there we go. Okay, so last time, do a quick review. I moved very quickly. We went through filters, and then we started talking about the Fourier series and the Fourier transform. Okay, different kind of filters: low pass, high pass, band reject. And their forms, do you guys remember what this graph was called? A Bode plot. There you go. Thank you. So Bode plot, which is a description of changes in frequency on the X domain to a magnitude change on the Y domain. Remember, the X domain was in what kind of a axis? It was logarithmic, and it was called a semi-log graph. Good job remembering those. Okay, so now you're going to see, you'll see these for amplifiers for op amps. If you look on an op amp data sheet, you're going to start to see these Bode plots. And in 2280, you're going to talk about what those Bode plots mean. You're going to see them with different components now. And now hopefully you understand what that means, is that over frequency, this is the response you get out of that component. All right. Okay, last time we talked about finding the transfer function. What was the transfer function?
H, and this would be out over V in.
Correct. So it's the output variable over the input variable. And so now it's talking about a generic input being put in. So we don't have a very specific one. It could be any input. What that ratio means is that your output now can be described. Say that V out over V in is 10, equals 10. whatever input, if it's a sinusoid, whatever input you put in, all you have to do is multiply it by 10. And that gives you an output. So it's a very powerful ratio of this output over input. For any input, you'll know you just multiply it by that equation. A lot of times it will be a complex equation like this though. And so it will be a little bit harder. So again, in 2280, you're going to go into more details about how do I look about this complicated equation and determine what the output is. So that will be a technique you'll look at in 2280. All right. Okay. So we talked about, oh, the other thing we talked about was Q, the Q factor. What was the Q factor? Do you remember the equation? Or what terms it was relatable to? It was what? Thank you. And omega naught was what? What? Okay. So omega naught was this is resonance frequency. So it is the very middle frequency called the resonance frequency. So this was a little different to cutoff frequency or corner frequencies. What was corner and cutoff frequencies? Remember what those were? So cutoff frequency and corner frequencies are the range between when the filter works. So for a low pass, it's the up to a certain point it will work. And then after that point, it no longer works. That point at which it no longer works is called that corner frequency or cutoff frequency. For the high pass, it works after that frequency. And that again is a corner or cutoff frequency. For the band reject and band pass, the middle point of that range is omega naught, which is that resonance frequency. And the corner frequencies is the range. It had two corner frequencies or two cutoff frequencies for band pass and band reject. Yes.
So, just talking about omega naught, since whenever we combined those band pass and band reject, what would our omega naught be?
If you did what?
We had both like combined band pass and band reject. Okay, like our omega naught be for like two individual.
Correct. So you would state it as two different resonant frequencies, the resonant frequency for the band pass portion and a resonant frequency for the band reject portion. And you would identify them as separate. And then you would also say the range that they're working would be separated too. So this would be your band reject section. This would be your band pass section. Does that make sense? Okay. So yes, if you have actual responses within one circuit that do different operating ranges, then you would just clarify what they do and what those values are. All right, so that will be the resonant frequency. So Q is going to be that resonant frequency over the bandwidth. What is the bandwidth? Bandwidth for the low pass filter is what? No? Okay. It's what? Correct. It's the area that works. So for the low pass filter, what will that range be?
0 to omega c.
Correct.
It's literally the length of the bandwidth.
Bandwidth, correct. So where it's operating, and so it would be from 0 to omega c in this case. What about for high pass?
Omega c is omega.
So it would be just above omega c. Just anything above omega c would be what you would say would be the bandwidth. Band pass?
Omega cutoff 2 minus omega cutoff 1, like the space in between.
Correct. Yep. So the area in between omega c1 to omega c2. And then band reject, you're going to say everything before omega c1, everything after omega c2. Okay, so those would be what you would say with bandwidth would be for those. Okay, so let's see. So then found H of S, which was your transfer function, and then found that this was a low pass. So for low pass and high pass, you still are able to get that like a spike, or you can even see some, it's called ringing, where it will oscillate as you're changing. So those will still have a omega naught and the bandwidth. Do you want for a low pass and a high pass, what value of Q do you want, a high or a low? Low. So for those, if your goal is a low pass or a high pass, typically you want them to be low so that it just rolls off very nicely and it doesn't do a spike. Remember, a high gives you a very narrow spike in there. And so you want a high Q for band pass and band reject, but the other two you want a low Q. So it depends on what your application is. You got to understand what value of Q you would want. So to get a high Q, you want a low or a high bandwidth. If you want a high Q, you want a low bandwidth because it's on the bottom, right? 1 over a low number gives you a really high number. And so that will be what you can play with is the bandwidth, but then you can also have control over where that omega naught is, and that will give you high and low values too. So you will always notice as a designer that you're going to have limitations. Like if you change the bandwidth, then your omega naught is also relatable to that. And so you'll need to have those as trade-offs. Okay, what was Fourier series?
Similar to Laplace.
Okay. And what was different than them? Do you remember? Like, why do you want to do Fourier versus Laplace?
You can represent
Oh,
a
sorry.
periodic function in terms of the infinite sums of sinusoids.
Correct. Is that what you were going to say too?
Yeah.
Okay. So what good is that? Any?
It can tell us how much contribution one particular frequency is in the signal.
Correct. So it gives us these kind of graphs, which are different than what we've seen from Laplace. So this amplitude spectrum shows you at different frequencies how much of an amplification it gives, or an amplitude it gives you. So you can see at omega naught here, like, oh, that contribution in the amplitude is the highest. And then for the phase portion of it, it then shows you the changes in the phases. So it gives you this graph. And for filters, you're actually going to see that it will be really high, and then all of a sudden it will drop off after the specific frequency. So you have pretty much just these spikes underneath where it passes on a low pass filter. And so depending on what your application is, it can give you this information. So we already talked about power, and the reason we now go to Fourier is because we want to know these contributions, and they become particularly interesting in power itself because, as I said, some of you had already heard, there's things called like the fifth harmonic, and that can contribute to effects on in a whole system that can be debilitating and actually bring down systems. So it used to not be understood as well. And so these lower, they call them lower harmonics. The first harmonic is going to be the most contribution. The second harmonic is going to be a significant, but not as significant as the first, and so on. And so you have these ones that are just very little contributions, but they will affect your whole system. And they can even like knock out a power system, which is not good. So that's one application. There's, again, other applications that this is going to be useful for. Communications is another area where you need to kind of understand these frequency differences. All right, so now let's look at actually how do we apply these to an actual circuit. So just like with Laplace, you've got the Fourier, and so the Fourier has the transformations, and so a delta function goes to 1, a 1 in the frequency domain goes back to a delta time, and so on. So this was a very common one we saw with Laplace, 1 over s plus some number translated into e raised to the minus number of t. And so here it's going to be similar. The a comes down and you have a S plus A basically. But we talk about in Laplace, we talk about J omega instead of S because we're more interested in each of those frequencies. So Fourier transform, as you can see here from the left to the right, also has both sides, however you want to say that. So it has the right and the left side too. So you want to call this, but anyway. Okay, so let's look at actually applying this. So these are going to be our first problems. So we want to find IC of t when we have Vs of t equal to 10 U of t. So to solve this, sorry, I'm going to get my notes up in a second. Maybe I lost my place. Okay, so we're going to change this over. Okay, so for Laplace, what would we do when we would solve this circuit? Okay. And then how would you use them?
Transform that capacitor, power source or current source depending on the initial value.
Okay.
And the capacity one over SC.
Okay, so for Fourier, what we're going to use is 1 over j omega c. So it's just replacing with the S with the j omega. So this is going to be 1 over SC, or it's going to be just 1 over j omega. The 2K, the 4K stay the same, and then we're going to translate the Vs of t the same way we did in Laplace, but we're going to do it now with the Fourier. So
Is there supposed to be a C there after the J omega?
yes. Thank you, sorry. Just okay, so now how are we going to solve this? Like what technique? You guys know me well now. Node voltage. Okay, so I'm going to label this as my node voltage. So I'm going to call it Vx here. And then I'm going to define all my arrows going out. And so writing this, what will be this arrow here? What will be that description?
Vx minus Vs to
Okay, the one going down.
Vx over T. Okay.
And then the one across the capacitor.
Vx over 1 over J W C or J omega C, where you can do it up to the top.
Okay, so I'm going to do this more generically. So I'm going to leave Vs in there. So I'm not going to change that over. And then I like to work with S. So I'm actually going to just solve it with S. And then I'm going to change it over to J omega at the end. Yes.
So when you do the class, we have to find the initial conditions to put a component with the meter.
Yes.
And you can Fourier
So in this case, yes. So we're going to assume 0, but you can see, so in this case, the U of t makes it very easy that everything is going to be 0. So we'll talk about that in a little bit. But we will assume that the initial conditions are 0 here. Okay, so now I combine my Vx's. And so I have 1 over 2K, 1 over 4K, and then CS. And then I move the VS over to the other side. And now I can divide by that. But first, I'm going to get a common denominator. So I'm going to use 4K as the common denominator. And so that will bring a let's see, that will be a 2 on the top for the 1 over 2K plus 1 plus CS 4K all over 4K. So when I flip that over to the other side, the 4K goes to the top, and then I have 3 plus 4K times C times S. And then this can be divided to give me a 2 on the top. And C in this case is 0.25 milli, so 4K times 0.25 milli gives me 1. So this then becomes 2 VS over 3 plus S. And then from here, we want to get IC was our end goal. So how do I get IC from this VX value?
I is equal to VX over, it's that current, right? So
Uh-huh.
over 1 over SC.
Correct. So IC will just be VX over 1 over SC or VX times CS. And so that ends up giving 2 VS 0.25 milli S squared. Or sorry, times S. 2 VS CS, there we go, over 3 plus S. This is a VS, yes. Is that what you were referring to, VS? Yeah, sorry, that was a VS. Okay, so then this is 5 times 10 to the minus 4 VS times S over 3 plus S. So this is my value, and then we can do the first one. So the Laplace of 10 U of t is going to equal 10 over S. And then I can solve this for the Laplace transform. 10 over S times 5 times 10 to the minus 4 times S over 3 plus S, and the S's cancel. And so translating that back for IC of t, I get 5 times 10 to the minus 3 e to the minus 3t u of t. And now for the Fourier, it's going to be done very similarly. The difference is that we replace the S with j omega. And so the equation is then IC VS times 5 times 10 to the minus 4 times j omega all over j omega plus 3. And then when we take the Fourier of 10 u of t, that equals grab it. So that then equals 10 pi delta omega plus 10 over j omega. And so plugging that in, we're going to get two components. So 10 pi delta omega times 5 times 10 to the minus 4 j omega over j omega plus 3, and then we add the 10 over j omega. And in this one, these are going to cancel. And now we want to translate back. The j omega over or plus 3 is going to be in the table. So that's going to be this one. And this one is a little bit more complicated because it doesn't have that. So we're going to actually have to find the inverse Laplace. So the inverse Laplace is this one. Show you a little trick. Comes kind of nice. So that's going to be 1 over 2 pi. Integrate this one, which is going to be 10 pi. And then you multiply it by ej omega t d omega. What is this? The delta function. Nice thing about the delta function, you integrate over it, goes to 0. It does not have any area underneath the curve because it's only a spike. So.
Will that always go to 0?
Mhm.
Every time I invoke the equation 13.6 can be.
The delta part of it goes to 0.
Delta.
So now all you have is the table that you can use. And so your IC of t goes to 0 plus, this is then 5 times 10 to the minus 3, e to the minus 3t u of t. And so that's then the same answer as the Laplace transform gave us. Yep. Okay, you guys ready to do your own?
Can we show the math from the integral to the 0 plus? I'm afraid I can't do that.
Okay, so this is what this is an averaging. And when you average a spike, there's nothing that will go away. That's 0. So then you're left with just this portion. And so you can use the table that has that transformation. And so you have 1 over a plus j omega, which is in this case, the a is 3. And then same properties as we had with Laplace. When you have a constant in the time, you have a constant in the imaginary plane. And so the constants just come out and multiply. Okay. Yes.
Can you just pick and choose which one?
What do you mean, which? Oh, which method? Unless you're told specifically which one to use. Yes, so they both, that's what I was getting at, is they both yield the same end result. So they don't tell you anything different in the method that's used. What can be told differently is then if we want to find the actual summations and graph those summations for the Fourier, then they can tell you more information.
I guess, okay, I realize my question. So you have IC is equal to the delta function plus the 10 over the omega time.
Yep.
Why did we only integrate a portion of that equation, but not the entire?
So this portion, you can use the table.
So it's just with some intuition, just like this part, I can just take and transform.
Well, if you were to write this out, you would have an integral of that first plus an integral of the second. But we already know what the integral of the second goes to based on that table. That's what that table is doing. Uh-huh. All right, other questions? Did you have another question? So the delta function, let me draw it. A delta function multiplied by any other anything still is going to be a delta function. And so an integral finds area underneath a curve. If there's no curve to it, it's going to go to 0. So that's why. Because of the delta function is why. Okay, other questions? You guys follow that? Yes.
If we have a situation where delta function does transform back into a time domain.
Yes, but we're not going to get into it. So in our cases, typically always we'll just integrate to 0. I'm not going to get into those other cases. Yes.
Okay, so going back to the Fourier transform,
Yeah.
we transformed the 10 u of t into that equation with the pi, delta omega, and then 1 over j omega.
Yep.
And then from there, you were able to split it up into the purple box and the red box.
Mhm.
Could you show me how you just did that again?
So I took this portion and multiplied it by the equation.
That's VS, right? The Fourier of the 10
Yes, this is my VS, correct. And so I just multiplied that in for the VS. And so,
there.
Yep.
But then where's the 10? Why is the 10 over j omega like? Is it,
so I multiplied this portion first. That's this first term.
Okay.
And then I multiplied this, the 10 over j omega with the equation 2.
Oh, okay, I see. Okay, so that was distributed, okay.
Yep, it's just distributed. Okay, other questions? Yes. Then- So this F omega is this portion here. So this one, I don't have to integrate it because the table tells me what that answer is going to be. So I'm just using the table to tell me what that integration would actually be without having to integrate the whole thing. You could, but I'll use the table. It's easier. Okay, that makes sense? Okay, and I saw another hand. Any other questions?
Can you do one more?
I'm gonna let you guys do one more. So the derivation is going to be the same, it's just your VS is going to be different. So now just do it for this VS when you have 10 e to the minus 2t u of t.
So I think earlier you touched on we could use the classical Fourier.
Uh-huh.
When would I want to use one over the other? Or it really is a 50-50?
It depends on what information you want from the circuit. If you want to get how much contribution is a portion of it giving me, if I'm modeling it by some signal and I've modeled it with a Fourier series, how much contribution is each one giving
I,
me.
okay, so I think like my monkey brain right now is just thinking of circuits in terms of like solve V out over terminals A and B. It's
Uh-huh.
like, and that is, you know, that's a lot of our homework is, you know, find V out. So like, is this Fourier analysis like separate to that? Like, or is this still a method to use to solve a V out?
It is still a method to use. Like you saw, the end results for IC of T is the same in both.
Okay, so this is just another.
It's another optional technique. It does yield more information for frequency portions of it. And so that's when you, if you want that type of information, you would use this. As you saw, this took me a little more effort to get to the time domain.
Right.
And so sometimes I may want to use Laplace is going to be simpler in terms of getting to an end result. But this will yield through the through the translation, it can also yield a Fourier series graph. And that can be helpful information.
That's very helpful.
Okay. So that's why we even want to look at it, is it can yield some more information for us.
Okay, so in terms of certain analysis, it's another tool, but in terms of, or in terms of our homework, certain analysis and stuff.
It's
but in
another
terms of
tool.
if you want to read a certain output, then one could be more informational than the other.
Yes.
Informative, okay.
Okay. So attempt to do this with the B.
Where in this equation would you be able to see Fourier graphs?
Not in this one.
Okay.
All right, so go, you guys good to work on doing B? Okay, try and solve this with B now as your input source. So that we've already derived the equation, so it's only the step of doing, this is my source now instead of the other source.
You always, like, when you go through this, you always go to Laplace. So that you can
I do.
Or can you go straight into?
You can go straight into Fourier, but then you have J omega in your equations and it just, to me, doesn't look as clean. Again, it depends, like if you're not able to match these up with like parts of the table and you have to actually do the integration, then you're like, okay, which one do I want to use? Yeah.
Something, so J is square root of -1, right? So if
Mhm.
like, well, if I go into it straight into Fourier, will I run into errors by perhaps having J squared that I solved as -1? Does that make sense?
Uh-huh.
Like,
Yeah, no.
will that cause problems?
No.
No, okay, so all the laws of math go through.
So what that J squared actually does is give you a phase shift because it will change it from positive to negative, which is a 180-degree shift. So it actually just tells you more information about the phase change than the magnitude change.
So if I were
So
to then
you're going to
launch-
still be the same.
Okay. So if I were to launch straight into Fourier and I see places where J's can cancel out and omegas can cancel out, that's okay.
Mhm.
Eliminating them. I won't.
Yep. Yeah. It will mean like there might be a pole and a zero at the same location and they're just canceling each other out. Yeah.
Apply that into this. You need for this.
Yeah, so the IC of T was because I did an inverse Laplace and an inverse Fourier. So this step right here, there was inverse Fourier
Okay.
to get to the IC of T. Actually, it's above here, so back up. So right here was where I did inverse.
I think it's a little plus, or no, I can't do it. Yeah.
Ian, to answer your question too, there is a table in chapter 13. It kind of gives a little bit more description of that. Oh, that was not the right one. Yeah.
So I've noticed that, as I've been doing some circuit analysis and get back into EE, I get a little bit of like math paralysis when I hit like situations like this.
Mhm.
So I just did a Fourier. I believe the transform is that. Oh, this will be a 2.
Yeah. So 10 over 2
Yeah,
percent.
yeah.
Yeah.
And so I have things in terms of J omega, and so this is my VS, this is that number, and then immediately I'm like, oh, this is super crazy, and
Yeah. So typically I like to take this number
uh-huh.
and just multiply it next to it. So. Great.
Okay, so I don't.
So. Put it in. I see that step, but like I would write it as 10 over 2 plus S, and then I would multiply it by the whole thing.
Okay.
S times, or sorry, 5.
Yeah, the S and the 5 always trip me out.
Minus 4 J omega. So it would look like this, and I like the look of this better.
Yeah, okay, that totally makes sense. So this would actually then go to the denominator.
Yeah,
then.
so then you can see that it's easier to multiply
That
those
is
two
a
together.
lot easier to multiply together. Okay.
If you wrote it in this form, you have to notice that this is this over 1.
Yes.
And so you would multiply the whole, everything
Thing.
by that, and so it'd be flipped up.
And then
you
it'd
can
become
see it.
exactly
Yeah,
that again.
then you could see that.
Okay, that's great.
But I tend to write like, okay, here's my VS.
Great, that makes
When it
sense.
has something divided by it, I'll just move
Move
it
it
out
out.
the front.
Ah,
Because you
okay.
can write it as VS times
1 over 5, yeah.
like that. So this is the same thing. So then I just multiply it by. Does that make
Okay,
sense?
that does. Okay, and you can move that out, and it'll be times 1 over that number.
Yeah.
Okay, cool. Because I think
Yeah.
I find myself getting needlessly complicated because that's harder to work with than that. Okay, great. I'll do that. Thanks so much.
Uh-huh. I'm hearing somebody say partial fraction expansion. Yes, you have to do partial fraction expansion. So Fourier is the same. You just, instead of S equals something, you use J omega equals a number. So it's just the same thing.
I got -0.01. And then. Yeah, I got Oh, wait, this is.
First off, 10 times that. And then this is obviously that. Getting an operating is 0.5. Oh yeah, I'm actually my. Yeah, it's point, you know, 0, 1,
Well, I talked with them a lot.
So, okay, so let me answer your question. Let me first answer your question about when we use the influence is how you decide here to here. So this is they just done the whole so that's where she showed you this, because like this is the actual thing. But you're never going to use this unless you're it's a the delta function. Oh, every time you do this, that
Okay. So we just got this part on.
when you check that,
Okay.
Oh, wait, our A's and B's would be.
Yeah, so then in this case, instead of like replacing that with the number, you're replacing the entire data.
yeah.
Okay.
Well, or whatever.
Yeah.
We have the same. Okay. That's a big.
Yeah.
Like, I got 15 times 10 -3 and negative 5.
Now I just do the transform and I can do a real, but. Yes.
Yesterday, I was so poor, I was doing about. I've been doing, but I was literally sure.
The competition is.
Also, like, I think it's a part of it, so I did it, I'm all over for sure. And then once you get to the next part, yeah, but I think a lot of still just take them off. That was a lot. My second time ever did it, that's the one.
That's when you get it.
What? That's like here. How are they doing this for you?
No, I mean like this. Is this supposed to be no fun? This building is. Everlasting. Yeah, and you see the partial is the same.
Just like to look at that. So you got.
Yeah, it's basically, the same idea as in the farm.
Okay, so I'm still down. It's probably, and then one that was good positive block. So you're good. This is I'm here to.
It's kind of giving you different information, so with these, we're looking at.
It's a sausage.
We can send you.
Yeah.
I think the majority.
Change it into the floss and change your S into J and like it's still.
So I'll talk about that.
Okay, so you got positive. This is so wrong. Like it's radiance. No, it's be per second. Yeah. Right. Oh, so I'm always. Isolate. As well as kind of saying. Yeah.
I lost my notes. I was just looking.
This one back. No, yeah. Yes, it's
Okay, so for this one, you can do Laplace and Fourier just like we did for the other one. So in Laplace, it transforms, the input transforms to 10 over 2 plus s. And so your IC is still the 2vs times s over 3 plus s over 4k, and then plugging in s or v of s of 10 over 2 plus s gives us this equation. So from there, you can do A and B as far as partial fraction expansion. And then you can get those values. And then changing those back into the time domain gives us 15e to the minus 3t minus 10e to the minus 2t milliamps u of t. So doing it with Fourier is very similar. The Fourier transform is going to be 10 over 2 plus j omega. And then you multiply that to get the IC of omega. And then again, partial fraction expansion. And here you're going to set j omega equal to either -2 or -3 to get that component. It will be the same values. And then from here, you can change it back into the time domain. And so you end up getting the equation either method in this case. Okay, so for these, we've had u of t as an input. Or questions about this before?
This is really bad practice. So I started off, I did a Fourier transform, and I got to where the IC of omega is that, but I left things in terms of S's. So I did a Fourier transform to start, and then I did an inverse Laplace to get back out. So
Uh-huh.
a lot of the problems doing that, doing like mixing up my Fourier and Laplaces, which I think consistent.
I would stay consistent, and where you're going to is where I'm getting next, like where the issues may come up is I'm getting to next. So we've talked about the inputs being of U of t, meaning that before time t equals 0, everything is 0 for the input source. So this becomes a limitation of when do you want to kind of use which method. So the information it yields for the phasor, if you guys remember for phasor, you could only do it for one frequency. So it was very limiting in that you could only know one input frequency and then determine it for that one input frequency. So yes, it's a good technique if you only are using one frequency. If it's over a lot of different frequencies and you don't know, then it's not going to be helpful to use. So it will do only a sinusoidal input too. So your input can only be a sinusoid, and then your output only gives you a steady state value for one frequency input. And so what is a transient? Do you guys know the term for transient?
Is that like from the 0 minus the 0 plus, like time t?
Correct. So it's right as something happens, what happens basically. So once I have a change in a circuit, right after that change is called the transient time, where it may fluctuate and then get to a period of time where it's like, oh, that's now always the same value. That's that timing where it's always the same value or always the same sinusoid is called the steady state. So the time period between when it gets to that point and when it first changes is transient. So phasor domain and Fourier series, again, gives no transient. And so we've looked at now Laplace. Laplace has been very powerful where it's any input. The limitations is that anything before time 0, you don't know. We've made an assumption that we just find it right at the value right before it switches. And so that's where we got that initial value. But what if it's not 0 before that? We only have that one time period, like right before 0. So it's called one-sided, and it will be limited just because you don't know before that time. So how do you define when something's continuously ongoing when time 0 really is? Because in a real system, do you interrupt it and then say, well, make sure everything goes to 0 and then restart it? You don't always have that ability. And so that's where the Fourier becomes to be more effective, because now instead of one-sided, as you commented, you see on both sides that it actually reflects. And so you have time before that and time after it. So that's when the power of Fourier, it doesn't assume any initial conditions, and so it's not limited. So they are the same as long as everything before time 0 was not there. So once it's not there, you can't use Laplace anymore. And so you have to only be able to use Fourier. And so that's where that becomes very powerful, is for any waveform input, and it doesn't need to have a time 0 defined. And so then you can get another complete solution for both, and transient and steady state information. Fourier also will yield that information about the frequency components, which is also another powerful one. So that leads us to the next input, where you have no U of t, so you can't use Laplace in this case. So in this one, you're going to find, again, you're going to have an integration, but when you see that delta function multiplied by anything else, you know that that one will integrate to 0. So I'll give you that hint. So go ahead and try and do part C of this one. Yeah.
So, yeah.
So this is only at zero is the zero, so this one goes to zero. But then these components,
Pretty sure they're on the table. Maybe I can see.
Yeah, like, what do I know? Once later, let's go.
they are on the actual.
I guess that's all then.
Let's if you're in, I'm.
This one. Will be this, multiply it, so let me. Check that. Let's see if I can find the options.
Yeah, you're looking at it.
So when you have.
I know.
Yeah.
So she says, what is wrong? I think you're yeah.
Oh, it's just, it just happens to be there.
Take your time if you're in the middle of something. Oh, I'm jumping the gun here, I'm sure, but like I'm immediately noticing there's delta, 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 and they're separated by pluses. So does that?
Yeah, so-
all those would go to zero?
No,
Okay, I thought, yeah, I haven't done any of the extra work. I just saw those and thought maybe I could separate.
integration, yeah. I was like, okay, maybe I need to, I didn't prepare for this one as well.
No
but I should
problem.
have. Interact of the function. Mm. But there are some properties of the delta function. I
That-
forgot to put it on there.
Okay. Okay,
I'm just trying to remember what they were.
no problem.
I don't think he put it. He talks about it in the book. So let me look it up. Then I'll look. Okay.
Oh, the five.
This is that's one of them. The right one. It's a derivative.
But how much times they have to use the delta with 0 and then multiply by that here, that the answer is 0. Yeah, I guess. Nice. It's not, there's no part of me that considers that a nice function. It says icky. It says icky. The item.
Nice function.
The COVID. Oh, second order.
Okay, I don't have an easy because I forgot to copy all the identities. So I'll work on getting those identities. Wednesday, we are not going to have in-person class. So I will post videos like I did last time where you can watch them on your own time. It will have a problem and then a solution and then a video solution. So it will have several problems to work through with the examples.
So are we expected to know how to integrate delta?
I'm gonna find simpler techniques to be able to look at these and be like, oh, that one goes to 0. This one is this value. This one is that one.
Okay.
So that was what I meant to do. And I thought I had copied them, but I didn't. And I don't remember where exactly I have them down. So
Okay.
I'll work on giving you a better, easy explanation and I'll do an example for Wednesday on this one. Yes,
Then to be clear, C is currently unsolvable.
correct. So I will go over the solution for C for Wednesday and you'll get a video of that one. And oh, yes. So I'll be on the Zoom link for our class. On Wednesday, I'll be on the Zoom link for our class during the class time period. So if you do have any questions, feel free to come on. And I will be here just on Zoom remotely for any questions anybody wants to ask. So it'll be the same Zoom link as our normal class period time. Yes, there was one more question over there. I have not posted anything for quiz. I can't remember what I said I was gonna do.
I'll try to read through this and then whatever I don't know,
I got farm C in here.
So there will be a discussion, no, there won't be. No homework, no quiz this week for Thanksgiving, so enjoy your Thanksgiving. Make sure to do the problems that I'll have for Wednesday.
I think I cannot make sure like you guys said. So I know if I multiply this term to this, it will become 0. But how can I?
I'm gonna find an easy way to explain,
Okay,
and I'll do a solution for Wednesday.
okay,
So don't worry about it for now.
okay, thank you.
Yes.
Hey, so, with that, like how you got the, Fourier equation,
Uh-huh.
like, are we gonna have any of those terms with like infinite series? Cause like, I noticed that Fourier transforms, we don't have like any terms in the Fourier transform that are a series.
Yeah.
If that makes sense.
Yeah, so, so here you can kind of see like, oh, these are giving some information in the Fourier about this as far as the summations.
Yeah,
So you can see in the Fourier graphs of these, like, yes, these delta functions, and that's what the summations always end up being. So your input signal will typically be a whole bunch of these cosines or a whole bunch
Yeah.
of sines. So you end up getting in the Fourier the graph of them. So then you can see the contribution of your input. And then you can also see before you translate it back, if you were to graph, I don't have it here,
Yeah.
but if you were to graph it, then you'll see that was what you were asking, like, how do I see those spikes?
yeah.
And that graph, that will be like right before you change back to the time domain.
Mhm.
You can graph that and get
Yes.
that information. from
Yeah,
that.
cause like
Does that make more
also,
sense?
yeah, that does. Also, like in math, we did like
Yeah, we're almost
the
there.
projection of